If you could remove every star, every planet, every atom, every last grain of dust, and strip reality down to what looks like absolute emptiness, you would not arrive at nothing. You would arrive at one of the most active things in the universe. Empty space is not empty. That sounds like a trick. It sounds like the kind of sentence physics uses when it wants to be clever. But it is not clever. It is devastatingly literal. Because for most of human history, reality looked simple. The world appeared to be made of things: stones, water, fire, bodies, moons, solid objects moving through a passive background. Physics, in that picture, was the study of how those objects fell, collided, broke, and turned. That picture worked well enough to build civilizations, but it was incomplete. The deeper we looked, the more the familiar world began to come apart. Matter stopped looking solid. Space stopped looking empty. Time stopped looking universal. And reality began to reveal itself as something far stranger than common sense had ever prepared us for. You feel solid. That seems obvious. Your hand meets the table. Your feet meet the floor. Walls stop your body. Every moment of ordinary life tells you the same thing. Matter is compact, substantial, and real. But when physics looked inside the atom, that certainty cracked. Atoms are mostly empty space. Their mass is concentrated in tiny nuclei. And what you feel as solidity is not little hard pieces of matter pressing directly against one another. It is the result of electromagnetic interactions and quantum rules that prevent matter from simply passing through itself. The world is real. Its solidity is real. But the picture your intuition gives you is not fundamental. Then physics went deeper. According to our best current framework, the universe is not fundamentally made of objects at all. It is made of fields. The electron field fills space. The electromagnetic field fills space. Quark fields fill space. The Higgs field fills space. What we call a particle is not a tiny marble traveling through emptiness. It is a local excitation of a field, a ripple with rules, a stable disturbance in something more basic than matter itself. Light is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Matter is not made of little beads. Matter is what fields can do. That changes the emotional meaning of existence, because it means that your body is not a pile of miniature solids. It is a stable pattern in a deeper fabric, not an illusion, not poetry, a physical structure, but one built from something far less intuitive than human beings ever imagined. And then comes mass. Mass feels like one of the simplest properties in the world. An object has more of it or less of it. It seems like a measure of how much substance is packed inside. But that is not really what most of the mass around you is. The Higgs field matters enormously. Without it, elementary particles such as electrons and quarks would not have the masses they do. But the protons and neutrons inside atomic nuclei, which make up most of the visible mass around us, get most of their mass from something else: the energy of the strong interaction, the confinement of quarks by gluons. So much of the mass in your body is not substance in the naive sense. It is energy, held in stable form. Inside every atomic nucleus, quarks are bound so intensely that the energy of that confinement contributes most of the mass. That is why Einstein's equation never stopped mattering. Mass and energy are not separate ingredients of reality. They are different expressions of the same physical content. So even your weight is stranger than it seems. It is not just a measure of stuff. It is a measure of energy, organized by law. And law, in physics, is often tied to something even more abstract than matter: symmetry. Some of the deepest structures in modern physics come from invariances, from transformations that leave the underlying laws unchanged. From those symmetries emerge conserved quantities, interaction patterns, and the architecture of the equations themselves. Symmetry is not decoration. It is part of why the universe is intelligible. And yet perfect symmetry would have left us with almost nothing to see. In the early universe, matter and antimatter should have appeared in nearly equal amounts. If balance had held exactly, they would have annihilated almost completely, leaving behind a cosmos filled mainly with radiation. No stars, no planets, no chemistry, no living observers. But balance did not hold. Some tiny asymmetry emerged. A slight excess of matter survived. Not much, just enough. Everything you have ever seen in the night sky depends on that discrepancy. Every galaxy, every planet, every living thing. Existence, in the form we know it, is built on an ancient imbalance. Then, scale shifts again. Gravity feels ancient and familiar. It governs falling objects, planetary orbits, the weight of your body. For most of history, it looked like a force pulling masses toward one another. Einstein changed that. In general relativity, gravity is not, at the deepest level, a pull through space. It is the geometry of spacetime itself. Matter and energy curve spacetime, and that curvature tells matter how to move. A planet orbiting a star is not being dragged by an invisible rope. It is following the straightest path available in a curved geometry. That idea shattered the old stage. Space is not just where things happen. Time is not just what clocks measure. Together, they form a dynamic physical structure, capable of bending, stretching, and evolving. The stage is part of the drama. And at the edges of what we understand, that structure begins to break under pressure. A black hole is not merely a dense object. It is a region where gravity becomes so extreme that our two greatest frameworks, general relativity and quantum theory, both become unavoidable, and still do not fit together into one complete account. Relativity describes gravity and large-scale structure with extraordinary success. Quantum theory describes the microscopic world with equal power. But in places like black holes, the two remain unreconciled. That is not a side issue in physics. It is one of the central, unfinished tasks. And it is far from the only one. When we measure how galaxies rotate, how clusters behave, and how cosmic structure forms, visible matter is not enough. There is extra gravity from something unseen. We call it dark matter, not because we understand it, but because we do not. When we observe the expansion of the universe, we find something even stranger. It is accelerating. Something is driving that acceleration. We call it dark energy, not as an explanation, but as a label for a cause we still do not know. These are not answers. They are names attached to ignorance. And yet their effects are immense. Everything you have ever touched, every atom in your body, every star ever seen by human eyes, belongs to the minority component of the cosmos. So physics becomes something more than a list of facts. It becomes a discipline of correction, a way of forcing the human mind to stop trusting appearances. It teaches us that emptiness has structure, that matter is excitation, that mass is organized energy, that gravity is geometry, and that the visible universe is only a thin disclosure of what is really there. And then, after all of that, comes the strangest fact of all. The same universe that produced hydrogen also produced stars. Stars forged heavier elements. Those elements entered planets. On at least one planet, chemistry became biology. Biology became nervous systems. Nervous systems became minds. And those minds began to ask what the universe is made of. A finite brain, built from ancient matter and structured energy, can infer invisible fields, detect particles that pass through entire worlds, estimate the age of the cosmos, and write equations describing events billions of light years away. That is not outside nature. That is one of the things nature does. Physics does not destroy wonder. It relocates it, away from myth, away from surface appearance, into structure, law, and the astonishing depth of what turns out to be true. The old hope was that understanding would make the universe smaller, cleaner, and less mysterious. The opposite happened. The more precisely we see, the stranger reality becomes. Solidity dissolves into fields. Matter dissolves into energy. Space and time become dynamic. Most of the cosmos disappears into dark components we still cannot identify. And yet the laws remain coherent enough that minds like ours can uncover them piece by piece. That is the deepest astonishment. Not that the universe is simple, not that it was made for us, but that it is structured in such a way that parts of itself can discover the rules by which it exists. We are still near the beginning. We can describe quantum fields with extraordinary precision, but we do not know why these fields, in this exact form, exist. We can track cosmic expansion, but not fully explain its cause. We can test relativity and quantum theory to astonishing accuracy, but we still do not possess a final framework that unites them. So physics is not finished, not remotely, and that is exactly why it matters. Because every time we go deeper, reality does not become poorer. It becomes more connected, more subtle, more resistant to simplification. The mystery does not vanish as knowledge advances. It becomes sharper, harder, more honest. Behind every object is structure. Behind every structure is law. Behind every law is a question not yet exhausted. And here we are, brief lives on a small world, made of ancient matter and organized energy, trying to read the grammar of a universe that was already old when the Earth was young. That is what physics really is. Not just explanation, but contact with reality at its deepest level.